Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to talk on the module Tight Binding Method for Electronic Structure from the paper Physics at Nanoscale. So students, let us see what we are going to learn in this module. Firstly, the tight binding method for the evolution of energy spectrum from atom to molecule and then to solid. Secondly, tight binding model explaining the electronic wave function and eigenenergy will be discussed. Thirdly, the procedure for obtaining the energy dispersion will be discussed in this module. So let us start with a basic introduction about the module. Similar to nearly free electron method for calculating the band structure, the tight binding model belongs in the class of methods based on independent electrons approximation. TBM or the tight binding model is the most popular method for realistic band structure calculations that takes the explicitly into account the presence of the periodic lattice potential. In contrast to the nearly free electron model, this TBM describes the electronic states starting from the isolated atomic orbitals. TBM can produce excellent quantitative results for bands derived from localized atomic orbitals. So, it is most appropriate when electrons they move through the crystal slowly, as it is the case in carbon-based nanostructures like carbon nanotube and graphene, in which the electrons are in some sense tightly bounded to the atom and only hop because staying put on a single or a simple atom costs high energy. TBM uses atomic orbitals as the basis wave functions. The energy spectrum gradually evolves as we go from atom to an assembly of atoms and then to form the solid. Now students, let us consider the tight binding method for a carbon atom. In a free carbon atom, the electron moves in a potential well as shown in this figure, where this part A corresponds to the evolution of the energy spectrum of a carbon from an atom, next to a molecule, and then to a solid. The atomic spectrum consists of a series of discrete energy levels which are denoted by 1s, 2s, 2p, etc. The carbon atoms contains 6 electrons, 2 of which occupy the 1s shell and 2 are in 2s shell, which are completely full, and the rest 2 electrons in the 2p shell. If the two carbon atoms are assembled to form the molecule C2 as shown in this figure, the potential seen by the electrons is now the double well. Due to a coupling between the atoms, each of the atomic levels, that is 1s, 2s, 2p, has split into two closely spaced levels, which are 1s, 2s, 2p, etc. molecular energy levels, which composed of two sub-levels. The amount of splitting depends strongly on the internuclear distance of the two atoms in the molecule. If the distance between the two nuclei reduces, the perturbation becomes stronger, leading to larger the splitting, which also depends on the atomic orbital. The splitting of the 2p level is larger than that of the 2s level, which is larger still than that of the 1s level. This is due to poorer overlap 1s wave function compared to that for 2s and 2p wave functions. It follows that, generally speaking, the higher the energy, the greater the splitting incurred. And this is clearly shown in this figure, where it is showing the schematic representation of the formation of tight binding bands as the spacing between the atoms is reduced. The above considerations may be generalized to a n number of carbon atoms. The carbon solid such as graphite, diamond, and nanostructure such as graphene and carbon nanotube may then be viewed as the limiting case in which the number of atoms has become very large, resulting in a large carbon molecule. Now here, each atomic level is split into n closely spaced sublevels, where n is the number of atoms in the solid. As n is very large, that is of the order of 10 to the power 23, the sublevels are extremely closely spaced so that the discreteness of the energy levels are blurred, resulting in the continuum band of energy known as energy band. And here, thus, the 1s, 2s, 2p levels gives rise to 1s, 2s, and 2p energy bands as shown in this figure above. The regions separating these bands are energy gaps, which is a region of forbidden energy. Generally, the higher the band, the greater its width due to strong perturbation, which is the cause of the level broadening. On the contrary, the low energy states corresponds to tightly bound orbitals, which are affected marginally by the perturbation, resulting narrower width of the band. So students, let us now discuss the tight binding formalism. In this formalism, the wave function can be written as a linear combination of fixed energy independent orbitals, where each orbital is associated with a specific atom in a molecule or a crystal. Here one assumes a form for the Hamiltonian and overlap matrix elements without specifying anything about the orbitals except their symmetry. Generally speaking, if n atoms are included in the tight binding model, the electronic wave functions can be expressed as a linear combination of block functions. So we can write it like this, that psi j as a function of k vector, r vector is equal to summation over j equal to 1 to n, c j j prime as a function of k vector, phi j as a function of k vector, r vector. Here Cij and phi j k r, they are expansion coefficients and block functions respectively, and this block function can be expressed as phi j as a function of k vector, r vector is equal to 1 by root n summation over capital R till n multiplied by exponential iota k vector dot capital R vector phi j, or we can say it as psi j, small r vector minus capital R vector, and here j varies from 1 to n. Here capital R is the position of the state and the psi j denotes the atomic wave function in the state j. Because of the translational symmetry of the unit cells in the direction of the lattice vector ai, where I can be 1, 2, 3, any wave function of the lattice psi should satisfy the Bloch's theorem. So we can write it like this, that T ai vector multiplied by psi is equal to exponential iota k vector dot ai vector multiplied by psi, and I can be 1, 2, 3, where TAI vector is a translational operation along the lattice vector ai and k is the wave vector. Phi j as a function of k vector, r vector plus a vector is equal to 1 by n summation over r vector till n over exponential iota k dot r dot k vector dot r vector phi j as a function of r vector plus a minus r. This is equal to exponential iota k dot a multiplied by 1 by n summation over r vector to n of exponential iota k dot r minus a multiplied by phi j as a function of r vector minus r minus a vector, and this is equal to exponential iota k vector dot a vector multiplied by phi j as a function of k vector r vector. Now here we use the periodic boundary condition for m is equal to n minus 1 by 3 unit vectors in each ai direction. Now phi j as a function of k vector r vector plus m a I vector is equal to phi j as a function of k vector r vector, where I varies from 1 to 3, consistent with a boundary condition imposed on the translation vector T m a I is equal to 1. From this boundary condition, the phase vector appearing in the equation satisfies exponential iota k m a I is equal to 1, from which the wave number k is related by the integer p by the formula, that is k is equal to 2p pi divided by m multiplied by ai vector, where p is equal to 0, 1 till m minus 1 and I is equal to 1 to 3. The eigenenergy Ejk of the jth band is given by Ej as a function of k is equal to the expectation value of h, that is psi j h psi j, divided by psi j, which is equal to the integral over psi j star h psi j dr divided by integral over psi j star psi j dr, where h is the Hamiltonian of the solid. After making the substitution for psi, we obtain the following equation, that is Ei as a function of k vector is equal to summation over j prime equal to 1 to n Cij star Cij prime multiplied by phi j h phi j prime, the whole divided by summation over j equal to 1 till n Cij star Cij prime multiplied by phi j prime, and this is equal to summation over j prime equal to 1 to n Hij prime as a function of k vector Cij star Cij prime divided by summation over j equal to 1 to n Sij prime as a function of k vector Cij star Cij prime, where Hjj prime is equal to phi j h phi j prime is the transfer integral matrix element, and Sjj prime is equal to phi j prime is the overlap integral matrix element, that is Hjj prime as a function of k vector is equal to phi j h phi j prime, and Sjj prime as a function of k vector is equal to phi j prime, where j and j prime varies from 1 to n. Now minimizing the energies Ei with respect to the expansion coefficients Cij leads to the following equation, that is del Ei as a function of k vector divided by del Cij star is equal to, in the numerator we have summation over j prime equal to 1 to n Hjj prime as a function of k vector multiplied by Cij prime divided by summation over j prime equal to 1 to n Sjj prime as a function of k vector multiplied by Cij star Cij prime minus, in the numerator we have summation over j prime equal to 1 to n Hjj prime as a function of k vector Cij star Cij prime divided by summation over j prime equal to 1 to n Sjj prime as a function of k vector Cij star Cij prime, the whole square. This multiplied by j prime equal to 1 summed over till n over Sjj prime as a function of k vector Cij prime. This is equal to 0. So this leads to the equation as summation over j prime equal to 1 to n Hjj prime as a function of k vector Cij prime equal to Ei as a function of k vector multiplied by summation over j prime equal to 1 to n Sjj prime as a function of k vector Cij prime, where Ci is equal to Ci1. Basically, it's a matrix consisting of the elements from Ci1 to Cin. And Hci is equal to Ei as a function of k vector Sci. Now here the band energies Ei can be determined from the generalized eigenvalue equation by solving the secular equation, that is determinant of H minus Es equal to 0, where the number of solutions is dependent on the number of orbitals per unit cell. Now let us discuss the procedure for obtaining the energy dispersion. In TBM, that is the tight binding method, the 1 electron energy eigenvalues, that is Ei, k, they are obtained by solving the secular equation. The Eik is a periodic function in the reciprocal lattice which can be described within the first Brillouin zone. In higher dimension, it is difficult to show the energy dispersion relations over the whole range of k values. So Eik is generally plotted along the high symmetry directions in the Brillouin zone. Using TBM, the band structure is calculated by the following steps. First, identify the unit cell and the unit vectors Ai. Second, then identify the coordinates of the atoms in the unit cell. Third, select the n atomic orbitals which will constitute the basis set for calculations. Lastly, specify the Brillouin zone and the reciprocal lattice vectors Bi and identify the high symmetry directions in the Brillouin zone and k points along the high symmetry axis. Next, for the selected k points, we need to calculate the transfer and the overlap matrix elements, that is Hij and Si. For the selected k points, then solve the secular equation and obtain the eigenvalues, that is Eik, where I varies from 1 to n, and the coefficients Cij, k. Tight binding calculations are not self-consistent calculations in which the occupation of an electron in an energy band would be determined self-consistently. Now, phi j as a function of r is equal to 1 by root n multiplied by summation over r alpha of exponential iota k r alpha multiplied by phi j as a function of r minus r alpha, where alpha can be a and b. Now HAA is equal to 1 by n summation over r prime, where or r bar of exponential iota k r minus r bar multiplied by phi a r minus r bar h phi a r minus r bar, and this is equal to 1 by n summation over r equal to r bar of epsilon to p plus 1 by n summation over r is equal to r bar plus minus a of exponential plus minus iota ka multiplied by phi a r minus r bar h phi a r minus r bar plus the terms equal to or distant than r is equal to r bar plus minus 2a. This is equal to epsilon 2p plus the terms equal to or distant than r is equal to r bar plus minus 2a. Now HAB is equal to 1 by n summation over r of exponential iota ka by 2 multiplied by phi a r minus r bar h phi b r minus capital R minus a by 2 plus exponential minus iota ka by 2 multiplied by phi a small r minus capital R h phi b small r minus capital R plus a by 2, where t is equal to phi a r minus r h phi b small r minus capital R plus minus a by 2, s is equal to phi a r minus r phi b r minus r plus minus a by 2. Now taking the determinant of the matrix, whose first element is epsilon 2p minus e, second is 2 multiplied by t minus se cos of k by 2, ka by 2, then 2 multiplied by t minus se cos of ka by 2, epsilon 2p minus e, and the determinant is equal to epsilon 2p minus e the whole square minus 4 multiplied by t minus se the whole square cos square ka by 2 equal to 0. Now this leads to the energy eigenvalues as E plus minus as a function of k vector is equal to epsilon 2p plus minus 2t cos of ka by 2 divided by 1 plus minus 2 cos ka by 2, where k varies from minus pi by a to plus pi by a. Now these figures, the first figure shows us the tight binding structure of silicon, that is the graph between the energy in electron volts versus the k vector, And the below graph shows the tight binding band structure of diamond. So students, let us summarize what we have learned in this module. First, due to a coupling between the carbon atoms, each of the atomic levels 1s, 2s, 2p has split into two closely spaced levels, which are 1s, 2s, 2p, etc. molecular energy levels composed of two sublevels. Secondly, the wave function can be written as a linear combination of fixed energy independent orbitals, where each orbital is associated with a specific atom in the molecule or in the crystal. Lastly, the tight binding calculations were discussed, which are not self-consistent calculations in which the occupation of an electron in an energy band would be determined self-consistently. Thank you.